everybody, my name is Tatiana and welcome to my video series on OTF Studio thin film software, a modern, smart and powerful software for designing, characterization, reverse engineering and monitoring of multi-layer optical coatings. In large area optical coatings, architectural glass and mass production, it's often essential to import and analyze measurements taken from various sample positions within a single reverse engineering workflow. In this video, I demonstrate how to rapidly import position-resolved measurement data into OTF Studio, perform comprehensive optical characterization, and visualize the results using two-dimensional contour maps. In this video, I will characterize a tantala layer on a big glass substrate. There are different positions, measurement positions. There are 11 vertical positions and 11 horizontal positions, and there is one central position. So we have transmittance measurements recorded at each position. And we assume that the tantala refractive index is known accurately, and the goal is to find thickness distribution of the layer on this big glass substrate. I open my OTF Studio project configured for this reverse engineering problem. So this problem should be solved in the reverse engineering mode. It's easy to switch between different modes using quick access toolbar. I loaded tantala layer material, one layer design, tantala material, and 150 nanometer thickness, and fused silica substrate. Now I need to import the measurements, import spectrometers, XY data, and in this folder I have 121 measurement files. Each measurement corresponds to one position, and the number of positions should be in the name of the file. So it can be vertical coordinate and horizontal coordinate. The format of the names can be different, but it's important to have these coordinates in the file names. Measurement data can be transmittance, reflectance, backside reflectance, and their combinations. So I mark one of them, open, and measurement import panel opens. And here we can see already imported 121 measurement files. It's important to have multi-scan mode, active, commit, and here in measurement editor we can see already all imported measurements for all positions, and we can switch between different positions, and we can switch between different positions in the preview. Edit text, and it's important to specify here position. So commit, and now we have one measurement data file, and inside of this file there are 121 measurements corresponding to different positions. We can load this measurement and switch between different positions. Now I open fitting plot, and if we switch between different positions, we will see these changes on the fitting plot. So fitting plot shows model, transmittance, and experimental data. The experimental data are simulated data. I focus on the reverse engineering model builder, activate systematic thickness model, and as I have only one layer and only one material, I activate systematic error in this layer and simply press batch processing tab and calculations started. In this fitting plot, we can see the progress. We can see fitting at each position. So at each position, we are minimizing the discrepancy function, the partial discrepancy function related to each position. And for each position, we are looking for systematic error. Very fast, we obtained results for all 121 positions. We can extract the results from history panel and observe discrepancy function and obtained fitting. Now I would like to summarize these results or visualize these results, and there are different options to do this. Batch, I can choose Batch tab on the View ribbon and New Contour Map. And here I can specify, for example, thickness of the layer. I have only one layer, but it works also for multi-layer coatings. And now we have a contour map, which shows thicknesses depending on position. This two-dimensional contour map provides an overview of how thicknesses, or there are different options, systematic errors, are distributed across the substrate. The map uses a gradient of colors to indicate varying levels of determined parameters. As one moves outward from the center, so we can see minimum deviation or maximum thickness in the center, and if one moves outward from the center, the deviation values gradually increase. The values of thickness. But of course, it's possible to display another diagram. It can be systematic thickness, or it can be relative thickness error, commit. The relative deviation shows that if we are close to the center, then thickness is close to the plane thickness of 150 nanometers. But if we move outward from the center, the thickness decreases. This is one illustration. Thank you for watching. If you have questions, feel free to reach out, and see you in the next video. Bye!